Okay, so welcome back to the second talk of this session. This will be given by Ek Thanathipanoonda from Mahidol University International College in Thailand, and he will tell us about the card guessing game, a generating function approach. Over to you.
Okay, so thank you. So I was a PhD. I was doing a PhD at Rutgers under supervision of the Doron Seiberger. I think between 2002 to 2008. Yeah, and then I actually met Professor Redgrave once. I think he came to Rutgers around 2003 or 2004. Yeah, so I remember very well. He gave a talk there. Yeah, and then about Dr. C, I was his student, and then he likes me to play chess and to play game. Yeah, so during the PhD year, we did some of the game together. Yeah, and then I feel like he would be actually he would love me to talk about anything, but I feel like he could be a little bit happier to see me playing games. So and then it just happened that today I got a topic about the game, so that I want to present today. Yeah, so this is a joint work with my colleague Tipalak Kritiyakriyan. Yeah, I think she's in the audience today also. Yeah. Okay, so this is a new work that we just finished. All right, so let me start that. Okay, so first we introduce about the blackjack game. Yeah, everyone's dream to win in the casino, right? So yeah, and then the most popular games like the blackjack. Yeah, we all know that blackjack, if we counting cards, then we can beat the house. Yeah. So for the blackjack, the dealer gonna do the rifle shuffle for a couple times, and then he or she like deal the card. Yeah, and then to take an advantage, as a player, we have to counting cards. Yeah, like when after the dealer deal the card, they we guess a card, and then the dealer turn up the card, show the card. Yeah, and then we keep track of the card that already shown. Yeah, and then we try to guess the coming card. Yeah, so that's the deal. Yeah, so what we are doing today? So similar to this blackjack game. Yeah, so we start with the deck that we know before rifle shuffle. So the deck is like order like 1 to n, like identity in the permutation. Yeah, and then the rule is we do the rifle shuffle k times. Yeah, I will tell you what exactly the rifle shuffle is. Yeah, and then we start to guess each card. Yeah, like we start guessing the first card, and then the dealer reveal the card, and then we and then we guess the second card, and then he reveal the card, and then and so on until the end of the deck. Yeah, and then the goal is to try to guess as to do the correct guesses as many as possible. Yeah, so that's the goal. Yeah, so we have two parts here. The first part is to try to figure out the optimal guessing strategy from the information of the review cards. Yeah, and then number two, once we have the guessing strategy, we have the distribution of the number of correct guesses. Then we try to see those distribution. Yeah, so two parts. Yeah, guessing strategy, and then the statistic of the number of correct guesses. Yeah. Okay. So first, we first mentioned about the rifle shuffle. Yeah. So rifle shuffle. This is the standard model that the mathematicians uses. So you have a deck of cards 1 to n. Yeah. So first you split it into two piles. With the you pick the top card, the top pile with t cards with the probability n choose t over 2 to the n. Yeah, so t here is run from 0 to n. Yeah. Yeah, so total probability is 1. Yeah, and then once you separate the top pile and bottom pile, then you do the rifle shuffle by interleave it back together. Yeah, like this. Yeah, like in the picture. Yeah, like in the picture here. Yeah. So yeah, so each of the interleaving, you know, like if you have top t cards n minus t, the number of ways to put them back together is like n choose t way. Yeah, so the resulting here, the probability of each of the resulting interleaving to show up is like 1 over 2 to the n. Yeah, so yeah, so this is the standard, like I said, this is the standard model for the rifle shuffle. This is the same model, maybe you heard of this before. This is the same model as the famous result of the Bayer and Diaconis, yeah, in 1992. Yeah, that said, you need to rifle shuffle 7 times to make the deck decks random. Yeah. So yeah, and then when he mentioned rifle shuffle, is this model, exactly this model. Yeah. What was first mentioned by Gilbert, Shannon, and Breeds. I think it's around 1950s something. Yeah. Okay, and then so this is the rifle shuffle model. Pretty simple. Yeah, pretty simple. Next one, right? So next one, so from now on we consider just the one-time rifle shuffle. It's because the 2 times rifle shuffle and more than that I will mention at the end. Yeah. So we will spend most of the time talking about one-time rifle shuffle. Yeah, and then I give you some example here. Yeah. So again, in here's a number of cards. Yeah. So if you have only one card, there are 2 ways to rifle shuffle it once. Yeah, only 2 ways. Like you have one card, whether you pick 0 card or you pick one card. Yeah, and then you put them back. Yeah, so there are 2 ways. Yeah. So but both ways it give you one and one. Yeah, here. Yeah, and then if you have 2 cards, you have 4 possibilities. Yeah, and then 3 of them will give you back the identity. Yeah, and then 1 of them give you 2, 1. Like you first you have 1, 2. Yeah, so if you split it and then put the bottom on top, then get 2, 1. Yeah, so that's it. Yeah, and then if you have 3 cards, then you have 8 possibilities. 8 possibilities, and you can see 4 of them are identity. Yeah, and then yeah, and then the other 4 is just another shuffle. Yeah, some shuffle. Yeah, so I want to make some observation here because we're going to use it later. Yeah, so these are example. Yeah, so let's see. So observation, number one, the number of ways. Yeah, number of ways. As already mentioned, if you have n card, you do one-time rifle shuffle. There are 2 to the n ways to do it. Yeah, 2 to the n ways, like in this example. Yeah. Okay, and then number two, the number of deck start with 1. Start with number 1. Yeah, you can see the number of deck that start with 1 is just the 2 to the n minus 1, right? Half of them, yeah, half of them, and then plus 1, right? Yeah, plus 1. Yeah, so this is some observation. Yeah, like n equal to 4, you see there are nine of these. Yeah, start with 1. Yeah, and then number 3, let's talk about the multiplicity real quick. Multiplicity for the identity that we have the multiplicity is n plus 1, like I mentioned. Yeah, n plus 1. Yeah, and then the others we have the multiplicity 1. Yeah, it show up only once. Yeah, show up only once. And also, if you look at it deeper, you see that the others that not identity, they have 2 increasing subsequence. Yeah. So for example, let me pick randomly 2, 3, 4, 1 here. We have 2 increasing subsequence, namely 2, 3, 4, and then 1. Yeah. So let's try another. Yeah, like this one. 1, 3, 2, 4. So you have 1, 2, and then 3 and 4. Yeah. So yeah, it makes sense because you split it into two pile, right? And then you put them back. Yeah. So they're gonna form like at most 2 increasing subsequence. Yeah. Yeah. So these 3 there are important properties that we're gonna use later on. Yeah. Yeah. Okay. All right, and then next one, the like I said, we're gonna have optimal guessing strategy first, and then we're gonna guess. We're gonna see the distribution of the number of correct guesses. Yeah, so the optimal guessing strategy is pretty simple. You start with 1, yeah, and then if it's correct, then go with 2, go with 3, and so on. Yeah, because let me go back. One is show up the most often, right? So you start with 1. Yeah, yeah, and then if the first one is not 1, then it means that the deck split into 2 piles already. Yeah, so then you guess with the longer subsequence. Yeah, you get with the starting number of the longer subsequence. Yeah. Yeah, I mean, yeah, right here. Yeah. So only 2 ways. Yeah. Start with 1. If the deck split into 2, then guess the first element in the longer subsequence. Yeah. Yeah. And then this can be proved that is the maximum the optimal guessing strategy is give you the maximum expected number of correct guesses. Yeah, I show you example also. Yeah, like this. This is the n equal to 4 that I mentioned earlier. Yeah. So with this strategy, say we pick this one. Say this deck 2, 1, 3, 4. So the first one we guess 1. So this one we not guessing it correctly. Yeah, but after the card number 2 is revealed, then we know that the deck split to subsequence like 1 and 3, 4. Yeah, so we're gonna go with the first element in the longer subsequence. So the second element we will guess 3. Yeah, because it's the first element in the longer subsequence. Yeah, so 3 is not here, so it's wrong guess. Yeah, and then we update. Yeah, 1 not here, 2 not here. So we have only 3 and 4 left. Yeah, so we can be sure that the next one we guess 3 and then we correct. Yeah, and then 4 is correct. Yeah, so like that. Yeah, and then we mark that the number of correct guesses as a random variable is the 2. Yeah. Yeah, not Yeah, let's do one more real quick. Let's do this one maybe. Yeah, 1, 3, 4, 2. Yeah, so the first one we guess 1 is correct. Yeah, and then next one we guess number 2, right? It's 1 correct. We guess number 2. Number 2 is not correct. We see 3. So we know that it's split it into 2 and 4. 2 and 4. Yeah, so it's equal chance. Yeah, if it's like this, then we guess the smaller number 2. Yeah, so it's not correct. Yeah, so but it's the 4 reveal, so we cross 4 out, so we get 2. Yeah, so we have two number of correct guesses. Yeah, so something like this. Yeah, and then you see the distribution of the x here. Yeah, like this. Yeah. Oh yeah, have to counting the multiplicity as well. Yeah. All right. And then, so the goal, like I mentioned, we have the optimal guessing strategy now. The goal is to calculate try to find the distribution of the number of x. Yeah. So we're gonna calculate the moment of x. Yeah. And then, yeah. What if we calculate many moments, we can see the distribution as well. Yeah. All right. So how to calculate the moment
Hey,
here?
let me ask a question. The blackjack is a very famous game, and there were some famous people who went to Las Vegas and beat it. So is that related? The optimal strategy, is it something famous before or something you made?
Oh, okay. Thank you for asking. This one, yeah, you usually the optimal strategy is very difficult. This one just for one time rifle shuffle. So this one is known before. Yeah.
Okay.
This one is simple because it's just one time rifle shuffle. Yeah, if they shuffle like 3 or 4 times, it's very difficult. I'm gonna mention it at the end. Yes.
Oh, because it's almost random. Yeah. Okay. Thank you.
Right. But one time we can still keep track. Yeah, because
Yeah,
you see that there are only two increasing subsequence. Yeah.
Thank you.
Yeah. Thank you for asking. Yeah. Yeah. So this thing that we mentioned now, it's just one time rifle shuffle. So yeah. Okay. So it could not be the Doron-Saarberger conference without setting up the recurrence, right? So this is we're gonna set up the generating function, and then we try to set up some recurrence so that we can manipulate our random variable easier. Yeah. So let dn be the generating function, yeah, of n cards. Yeah, and then q is the I here is the number of correct guesses. Yeah, and then ai is like number of decks that have this many number of correct guesses. Yeah, and then you can set up yeah. So let me call it. This is Saarberger number 1. Yeah. So try to set up the recurrence relation. Yeah. So so if this one I mentioned, if the first card is 1, yeah, then you stick the Q here. Yeah, and then you can do the recursive relation here. Yeah, and then if the first card is not 1, then it means split it into 2 increasing subsequence. Yeah, and then we call it the F. Yeah, we call it F. Yeah, so the number I here is the number of first card that's shown. It's I will tell you. Yeah. So this is the example. Yeah. So for n equal to 4, yeah. So if the first card is 1, then you see you can just shift the rest, and then it will match with the n equal to 3. Yeah. So yeah, and then you plus one more element here. Yeah. Yeah, and then if the first card is not 1, yeah. So say it's like 2, then it's split it into 1, 1, and 3, 4. Yeah, and then we call it F1, 2. Yeah. If the first card is 3, then it's split to 1, 2, and 4. We call it F21. Yeah, and then last one you get 3 and 0 right here. Yeah, so the generating function can be calculated by this recursive relation. Yeah, but we don't know what F is yet. Yeah, so the F here can be calculate through another recursive relation. Yeah, so let M greater or equal to N. Yeah, so we're gonna guess M, right? Because it's a longer subsequence. Yeah, so we guess M. If M show up, then we have Q here, and then M go down by 1. Yeah, and then if M is not show up, then we didn't guess correctly. Yeah, and then N go down by 1. Yeah, so this is the recursive relation. Yeah, so in one sense, this is another version of the Q binomial. Yeah, another version of the Q binomial. Yeah, and then this one I think I never seen it before. So what I did, I just ran the program on this, and then I just try to find the patterns on the Sloan. Yeah, so it turned out that the F, M, and Q can be written in the sum like this. Yeah, in this form. Yeah, yeah. So this is the second achievement here. Yeah, so we have the formula for F. Yeah, and then right, and then once we get the F, we combine it with the Q to the N, and then call it G and Q. Yeah, so this G yeah, so you see from this, sorry, I go back a little bit. Yeah, so you see from this this relation. Yeah, so you have D and Q is Q D N minus 1 Q, and then plus G and Q now. Yeah, so this whole thing is like a G and Q. Yeah, so yeah, so once you know the formula for the capital F here, we can we have the double sum, and you can switch the order of the sum. Yeah, and then you can get the closed form formula of the G, the Gn differentiate R time. Yeah, and then plug in Q equal to 1 also. Yeah, so yeah, so it becomes a nice formula like this. Yeah, and then you see this one is the binomial sum. Yeah, this is the binomial sum. So the summation here, it can be it will give us the closed form. Yeah, you plug in the specific R. If you want to differentiate R time, you plug in a specific R. Yeah, then you get the formula in terms of K. Yeah. So in this case, we have to split N into 2 cases, even and odd. Yeah. Yeah, and then the index here is not go all the way. Yeah, from 0 not to K minus 1, just K minus 1, but it go like exactly half. So we can we get we can still get the closed form. Yeah. Yeah. So okay, so now we can, once we know the Gn differentiate R time Q looks like, then we can calculate the factorial moment. Yeah, so this is the method that Professor Seiberger used all the time also. Yeah, so differentiate R time, and then you know, get the factorial moment. Yeah, so yeah, so here step 1, you get the Gn by this formula. Yeah, and then step 2, you have something like this. Yeah, so once you know the formula for Gn, then you can use the and then we know this also because the say we do it for like I equal to 1 to 2. Yeah, so we know this term also. Yeah, so now you got the difference equation. Yeah, and then you can use a method of undetermined coefficient to solve for dn, to solve for this solution. Yeah, and then once you get the d, you divide it by 2 to the n, you get the factorial moment. Yeah. So I give an example real quick. Yeah. So for the first moment, yeah. So for I equal to 1, yeah. This is the G prime. Yeah. And then you plug it back to the original equation. Yeah. So you get the equations look like this. Yeah, and now you use the method of undetermined coefficient. Yeah, with this term and this term. Yeah, this term is small, you can ignore it. Yeah. So yeah, so the first term you guess like this form. Yeah, and then the second term is harder because you have the central binomial here. So we have to expand it using to like infinite series approximation first, yeah, and then the answer that we use for the NQ is like something like this, yeah, and then you use a computer to solve for the constant, yeah. So yeah, so you get something like this, yeah. You can specify how many terms of accuracy you need. Yeah, so this is what you get from the first term. Yeah, and then this is what you get from the second term. Yeah, and then you just to get the expected number, you just divide it by 2 to the n. Yeah, so you get something like this. Yeah, at the end. Yeah, which I think makes sense because you know, like you got it. The number of cases correct about half of the time. Yeah. And then but the card is revealed to you each time. So this is the advantage that you get. Yeah, so you get like some extra advantage here in terms of like a magnitude of like square root n. Yeah. Yeah. All right. And then I try to, once we have this method, we can calculate as many moments as we like. Yeah, so you calculate the factorial moment, then you turn them into the raw moment. Then from the raw moment you can calculate the moment about the mean. Yeah, so yeah, and then you can tell whether the x here is normal distribution or not. Yeah, but from here you can tell already that the distribution is not normal, right? Yeah, it's not normal because the third number here is they're not 0, so it's not symmetric. Yeah, so so this is the picture that my colleague made. Yeah, so it's clearly that for each different n. Yeah, so it's clear that the distribution of the number of correct guesses, the x here is the kind of like skew to the right. Yeah, you see that the mean is kind of like to the right of the peak. Yeah, so this is skewed to the right. Yeah, so
you're almost out of time. Maybe you should.
Oh, finish. Okay. I thought it started 45. Do I?
No, 42.
42. Okay. Yeah. Okay. I'm done anyway. Yeah. So yeah, and then like Dr. C said, although it's like for k equal to 1, yeah, so for k more than 1 is the it is very difficult, and then it's still open, yeah, still wide open, yeah, but I think it's quite a difficult problem, yeah, because we don't have the optimal guessing strategy yet, yeah, let alone the generating function, yeah. Okay, so yeah, and then this is the reference, yeah, so happy birthday to Professor Rikev and Dr. C. Yeah. Thank you.
This is very interesting, even with one rifle. But so poor Gauss. So the limiting distribution is definitely not Gaussian. But did you look at the first few moments? There are many other, or quite a few other distributions out there. Aaron knows of quite a few of them. So did you recognize the limit distributions? Is it some
It
other
looks like
name
it's have a square root and pi. It's have a square root and pi. I ran the program up to like r equal 12, like 12 moments. But the leading term is like come up with like square root and pi. So I don't really know it fit into what distribution. Yeah.
So you couldn't recognize it as a named distribution. So it's a new distribution
No.
then. Oh, okay, so
Yeah, I
you
have
could
no
name it after
idea.
yourself. Okay, thank you.
Okay. Yeah, so it's like yeah.
That's very nice.
Okay, yeah. Yep. Thank you, Dr. C.
Okay.
Any other questions? So I had a question. Something is bothering me about your generating function. I thought your generating function just counts the number of cards. I mean, according to the position of, according to
So
I,
it is
the
no,
number of guesses.
let's see.
I mean, I'm just looking
Right.
at
So
your
you have to the end deck, right? And then each deck you count like how many correct guesses. You
right,
have
but
many decks.
you also need to know the probability of every. I mean, this is not uniformly distributed, right? I mean, as you yourself showed in a table a few pages ago, you have different for n equals 4 or something.
Oh, okay. Right.
Different
So
probabilities.
So this one has been done 5 times. Yeah.
So you're overcounting. So that.
Right.
Okay.
Right.
Okay. Thank you.
Yep.
And
Thank you for asking.
Another question.
Yeah, that's why we have the plus here. Yeah.
Another question I had. So have you? So do you know this connection between riffle shuffles and linden words? So
No idea.
So I think so. There's an earlier paper of Diaconis, I forget with someone else, where he shows that if you, I mean, the distribution of cards after a certain number of riffle shuffles, maybe 2 or 3 or something, or maybe even in general, is related to linden words. And if that is the case, I mean, I don't remember if that will help you. I mean, I don't remember the details, but if that might help you, then you might be able to do this for general number of riffle shuffles. If you want, I can try and find that paper.
Right.
But there is but do you know this connection between riffle shuffles and linden words?
So no.
Let me type.
Yeah. So in his famous 1992 papers, I saw that he tried to mention like K-time rifle shuffle. Yeah, but he got stuck also. Yeah, so that's my impression. But I'm not sure if he have any.
Before that. This is before that. I'll find.
Okay,
I'll try to find.
Then it's yeah. But in 1992 he mentioned that he got stuck also. Yeah.
Okay.
Yeah, with this model. Yeah.
Okay. Thank you. Okay, so I guess the next talk.
Thank you.
We'll meet in 5 minutes, unless there are any other questions. Okay, let's thank Ek again for a very nice.
Thank you.
So.